So, good evening, everyone. We are Group 2. Myself, Akshat, and my teammates are Dilip, Vedant, and Krishna. Today, we are going to talk about supply chain risk analysis using the Neo4j, which is based on a graph data modeling for like predictive and relational insights into global supply chains. So, in an era of global trade where it is like more interconnected than ever, supply chain distributions have become a major business challenge. Whether it's geopolitical conflict, a factory shutdown, or even a pandemic, everything from phones to food can be affected. So, our project tackles this by modeling a supply chain using Neo4j, that's a graph-based NoSQL database, which treats relationships as first-class citizens. This allows us to go beyond the traditional databases and perform meaningful analytics like risk flows, centrality, and path distribution. So the reason behind choosing Neo4j as a core topic for the project is because that it understands data not as isolated boxes of like some data, but as a web of context, which is perfect for how supply chains actually work. So over the next few slides, I'll introduce the motivation behind this work, objectives we set to achieve, and how we structure our data to represent this kind of real world network. Then in the later part, my teammates will dive into the implementation, analytics, and the outcomes of the project. So let's begin with why we took this project. The biggest trend in supply chain is how interconnected they have become and correspondingly how fragile. A problem that one supplier can cause cascading delays that affect like entire industries. Just think of how a 2020 semiconductor shortage impacted everything from like cars to computers. The problem is most traditional databases don't show us these connections. They are great at storing lists of suppliers or products, but they struggle when we want to take like deeper questions. Let's say, what are all the paths connecting a higher risk smelter in Africa to a retail supply in India? Or uh, which upstream relationships would be impacted if like one shipping hub gets blocked? So this is what motivated us to explore Neo4j and its capabilities. So Neo4j models data not into the rows, but in nodes and relationships. This lets us map a supply chain as a graph and then use the like various graph algorithms to analyze risks, dependencies, and bottlenecks. So the core idea behind this like topic selection was we don't just look at what each entity is, but how it's connected. That's where the real story and the context of the data lies. So understanding these patterns can help the business strengthen their resiliency, improve delivery commitments, and better forecast impact if something is going wrong. So now let's talk about the motivations and objectives. So based on the issues and uh, the things that I discussed in the previous slides. So there are some issues in this field, and our interest in graph modeling set us three main motivations for this project. First is to simulate a realistic supply chain scenario with nodes representing companies or products and relationships showing how the actions like product flow or regional grouping is done. Second is to write an automated generator tool that creates synthetic data because the real world supply chain data is like often sensitive or kind of proprietary. So our generator helped us to produce data for smelters, suppliers, and products, including properties like location, risk category, and the type of the product. The third is to use the power of graph analytics to answer complex questions like who are the most connected suppliers in the ecosystem, what is the shortest path between the two stakeholders, are these graph of nodes that form communities based on any attributes, which nodes would be most critical to protect from disruptions. So the core objective from this structure was that we were able to do the following from it. first use Neo4j to model the model and visualize the supply chains through nodes and relationships. Automatically group and connect nodes based on shared risk levels. Also based on the geography and interactions. And third was to allow the extraction of insights using different algorithms such as degree centrality, community detection, and path finding. So here we build an interface to interact with the graph through different queries and reports. So all of this together lets us compare the Neo4j's structure and performance against a relational database and build foundation for deeper predictive, or let's say a real-time monitoring in the future extensions of it. So when we see a data set and we set the goals for it, so let's look at how we basically structure the data set. So our data set contains mainly of like three types of primary entities. First is the smelters that I'm talking about since the first slide. So smelters are the one that represent raw material like processors like aluminium, copper plants, etc. Second is the suppliers that represent an intermediate step, uh, like companies that deliver or produce goods. And third is the products, that's the final manufactured product or the components. Each of these nodes has attributes. For example, smelter has, let's say, smelter has a name gamma materials or gamma metals. It's from country China. Its risk level is high. So, and will need a capacity for the smelter as well, right? So let's say 200 tons per week. So these are the nodes which are then connected by relationships like supplies, produces, or located in, like I mentioned, from the different attributes that I already talked about. So these nodes are connected by relationships like supplies, produces, are located in, and a supplier node may supply a smelter or a product may be produced from a given factory. These relationships brings a graph to life. So using our advanced data generator, which we used in the final submission of this project, we produced over 100 nodes and 300 to 400 relationships. The number of nodes and connections scales linearly depending on the input parameters. The generator also added some unique constraints and indices for efficiency. And for the final stage, we added a smart relationship logic. So the smart relationship logic works in a way that if two smelters are in the same country and they are, automatically given the same country name for the relationship. So if they share a risk category like very high, they are grouped with a same risk link. So this feature allowed us to create regional and risk-based clusters, which becomes, very useful for community detection and for risk simulation as well. So through this structure, we essentially build a graph that behaves like a mini world supply chain where you can interactively explore the relationships, locate different vulnerabilities, and generate dynamic paths and reports for the same. So moving on in the next part, my teammates will deep dive into the main analysis of this project and what all work did we do to, work on these challenges. Thank you.
Hello, my name is Dilip Kumar Sharma, and today I'm going to walk you through our Neo4j supply chain project. And I think you'll see why graph databases are genuinely game changing for this kind of problems. So let's start with a big picture. Our project models a real supply chain network. We are talking smelters, suppliers, products, and distribution hub all interconnected. Now, if you try to visualize this in a traditional relational database, you would have a bunch of tables with foreign keys, and honestly, it would be really hard to understand the relation at a glance. But with Neo4j's graph visualization, you can see the network. You literally see how one supplier connects to multiple smelters, how smelters feed into different products, and how everything flows through the supply chain. This isn't just pretty, it's just functionally important because supply chain risk is all about understanding these connections. If one smelter goes down, you need to quickly see what products are affected and what alternative suppliers exist. The richness of our network, what we call node and edge diversity, lets us demonstrate both breadth and depth. We can show variety across different entity types, and we can trace multi-hop connections, like show me all the product that depends on smelters in a high-risk region, 3 levels deep. Okay, so what makes a Neo4j actually fast at this? It comes down to how it stores data. Neo4j uses what's called native storage instead of suffixing everything into generic table row. It has specialized fixed size records. Node records are 15 bits, relation records are 34 bits. This might sound like a small detail, but it means Neo4j can calculate exactly where data lives on disk using simple arithmetic, no search required. The real magic is index-free adjacency in relation database. When you want to find connected records, you have to look up an index, scan through it, and then retrieve the matching rows every single time. But in Neo4j, relations are stored with points directly to the connected nodes. So when you traverse from one node to another, it literally just follows a pointer. This is constant time, no matter how big your database gets. And then there's memory management. Neo4j uses a LRU page cache with something called as scan resistance, which prevents big sequential scans from evicting your frequency access hot data. It also does dynamic prefetching. It learns your access pattern and preload data with things you will need next. Now let's talk about actually querying this database. Neo4j uses Cypher, and honestly, once you get used to it, it's so much cleaner than SQL for graph queries. Let's look for an example over here. So find all low risk smelters 2 hops away from a high risk node. In SQL, you need to multiple self joins, subqueries, probably temporary tables. You're talking 40 plus lines of code. But in Cypher, 5 to 10 lines is enough, and it's declarative. So you describe what you want, not how to get it. Behind the scenes, Cypher goes through a full pipeline: parsing, semantic check, logical planning, cost-based optimization, and finally execution. The optimizers looks at your indexes, estimate cardinalities, and pick the most effective execution plan. And the performance difference is dramatic. In our testing, the 2-hop query on the low-risk filters under 15 milliseconds in Neo4j. The equivalent in PostgreSQL in seconds. That's not small difference. That's an order of magnitude. Finally, I want to show you how we automated relationship creation, because this was one of the cooler part of the project. We built smart automation that look at node attribute and automatically creates relationships. For example, if 2 smelters are in the same country, it creates a same country relationship. Same for the risk level. These aren't relationships we manually defined. The system discovers them, and we made sure this is future proof. We are using element ID instead of deprecated ID functions, so our code is compatible with Neo4j 5.x and beyond versions. We also built in comprehensive error handling and performance tracking. We created a command in our CLI called create art relations that you can run anytime, and it automatically scans the database, finds these logical connections, and creates them. This keeps the schema evolving as the database grows. So to wrap up, Neo4j gives us visual clarity for complex networks, performance that scales with connected data, intuitive query syntax, and intelligent automations. For supply chain risk analysis or any other domain where relationship matters, graph database aren't just better, they are essential. Thank you.
Today, and I'll speak about hub nodes and topology enhancement. One of the most powerful enhancements we made to a supply chain network was the introduction of hub nodes and topology enrichment. We implemented 3 types of hub nodes in our system. Firstly, we have geography hubs, that is, we are classifying the smelters by country hubs. So you have a USA hub, you have a Chinese hub that connects all the USA based supplier smelters to the USA hub, and the Chinese based suppliers to the Chinese hub. Secondly, we created risk hubs, that means that we have multiple hubs with the risk, low risk, medium risk, high risk, and critical risk. This adds finally we have a central hub that gets connected to all the entities providing the star topology. The benefits this provides us is that the hubs transform how we query our data. Instead of writing complex queries for finding, let's say, high-risk smelters, we can now just simply query the high-risk hub and get the results directly. This and another thing is, like, instead of querying for a country as well, you can just query the country hub and it will return all the all the smelters for that country. This is what we mean by group by country or group by risk analysis. It's essentially pre-computed aggregation through graph structure. For example, let's take in one of our implementation codes with 100, we have 119 nodes and 1277 relationships, which serve as network landmarks. So when we run our hubs, it automatically creates geographic and risk hubs and establishes all connections. This takes down our query times, which would traditionally have taken a long time for the, let's say, minutes, to now mere seconds. The topology enrichment makes our visualizations immediately actionable. When people see these graphs, they can instantly spot clusters of high risk node, medium risk nodes. This is particularly powerful because when we do our analysis, we can immediately classify the high risk smelters, and on those basis identify supply chain gaps. These hub nodes don't just organize our data, they fundamentally change how we approach supply chain risk analysis, making complex queries simple and insights immediately actionable. Let's now talk about the graph analytics feature. We implemented our extract actionable insights from a supply chain network. First degree centrality. This is a measure of node importance. In our implementation, we calculate how many connections each smelter supplier or product has. High degree centrality identifies critical hubs in the supply chain. For example, in our dataset, we discovered that certain smelters act as central distribution points with 20 to 25 connections each. These are your single points of failure. If one of these high centrality nodes goes down, a large part of the network is affected. A Python implementation uses a simple but powerful cipher query. We match all nodes, count their relationships, and sort by degree. This helps us to pull down work which would have taken like minutes to mere seconds again. Second is the shortest path analysis that we have done. This is crucial for what if scenarios. Let's say we have a high risk smelter in China, and you from that particular smelter, which all other entities would get quickly affected. Shortest path tells us the minimum number of hops to reach any other node. In supply chain terms, this represents the fastest propagation path for destinations. Uh, because like we talked about earlier, using the different types of hubs that we had, we can easily identify which hubs are connected to high risk smelters, and using them find the path propagation from there. Third is community detection, identifying isolated groups or clusters. This is essential for resilience planning. If we find a clusters of smelters that are only connected to each other with no external links, that's a vulnerability. These isolated communities share common suppliers or geographic locations, creating concentrated risk. This analysis, we discovered that certain countries had highly interconnected domestic supply chains but weak international connections. This insight directly translates to recommendations like diversifying our geographic sourcing or creating redundant paths across regions. All three analytics are integrated into an interactive CLI. You can type centrality smelters and get immediate results, or autofix to create optimal relationships and then analyze the improved network. This makes complex graph algorithms easier to understand to people not of the particular fields or outside stakeholders. These three analytics, centrality, paths, and communities, give us a complete picture of how the supply chain held vulnerabilities and opportunities for strengthening resilience. Let's now talk about visualization of the risk and geographic cultures. Visualization is where the graph databases truly shine. Let me explain how color-coded visual clusters translate raw data into actionable business intelligence. We implemented a dual color coding system in our visualization. First, geographic color coding, where each country gets a distinct color. You can see that all particular smelters of a particular country, let's say for example USA, are yellow, or let's say Germany as red. Second, risk level color coding, where critical risk nodes might be red, high risk might be orange, medium risk yellow, or low risk green. When you look at the graph visualization from a network, the image we showed earlier with 119 nodes, you can instantly identify patterns. Are all your high-risk entities clustered in one region? Do you have over-dependence on a single country? These insights would take hours using other SQL-based structures, but to us, using a Neo4j database or a graph database, this is available to be visualized in just mere seconds. The visualization helps us identify two critical vulnerabilities. First, over-centralized segments. These are densely connected clusters where one failure cascades rapidly and could result in the entire supply chain from that point on going dark. In our network, we found certain geographic regions where suppliers, smelters, and products from tight loops. Second, isolated nodes, entities with few connections that could benefit from redundancy. Let's say from our examples, we had a 1200 centizen relationship network visualization that we created. Medium risk entities were most geographically diverse. So whereas high risk ones were concentrated like in a particular country or a particular region of a country. Using visualization, we can identify them, which region is highly risk critical, and as such we could explain to our stakeholders or a person viewing the graph that why they should avoid supplies from those particular reasons. The third point that we would like to raise is stakeholder communication. This is game changer for presentations. Like in terms of stakeholding, we can show executive spreadsheets and with supply chain list. You can literally show them a graph where they can see the entire supply chain, map it, identify what critical junctures are there, where is the redundancy part available, what is let's say critical path, whereas there is only one path available. These the thick connection lines that we have show major dependencies, while isolated clusters show diversification opportunity. Let's say, for example, we present this to a COO and they spot that all their suppliers are located in China and are in high risk area. Therefore, they can visualize using our graph and then take alternative routes, alternative decisions, and identify which other areas where they can provide redundancy to, so as to avoid a cascading rapid failure. Visual clustering transforms complex supply chain data into intuitive, actionable insights which anyone can understand, from data scientists to other like executive level people. Let us talk about risk propagation and key results that we derive. Risk propagation is about understanding cascade effects. Our implementation can answer questions like, if this high risk supplier fails, which low risk entities within 2 hops can get affected? This is a multi-hop traversal query that is very difficult for other relational databases, but for a graph-based database, it is very easy and trivial. Let's say understand this with a example scenario, shall we? Let's say we want to let's say we have a high risk smelter in China and it goes down. Then we can understand then we want to identify which low risk smelters will be affected that are within 2 supply chain steps of it. Using a graph based database and visualization, we can easily identify it and as such understand the pathways much better. The other question we have is our choke point discovery. Our analytics reveal that centralization choke points. Choke points are particular points that have a single pathway through them, and there isn't a path that goes around it. So if, let's say, a choke point faces difficulty, the entire business or the supply thingy that goes through those points and the points in the connected steps fails, and as such that part of a supply of a business goes offline. So it's an issue, but using graph-based databases we can identify the choke points, and as such when a stakeholder or an executive looks at them, they can find alternative routes around them so that they have as less choke points and as such as less vulnerability as possible. Let's talk about recommendations. Using our analysis, we are able to understand different parts like cross-link isolated clusters, or clusters that are weakly connected to the entire other database. Low dependency or individual hubs like supercritical hubs that we identify, and we recommend redundancy planning, alternative suppliers, backups, etc. From business value, we are able to create understanding modules that, sorry, my laptop just shut down. Sorry. Yeah, we are able to create, from business point of view, we are able to create individual value to smelters and nodes, and as such create insights and actionable plans for them to implement in the future. So our bottom line is that the Neo4j doesn't just store supply chain data faster, it enables entirely new approaches to risk management. We move from reactive reporting to proactive risk intelligence, from static snapshots to dynamic simulation, and from data storage to decision support. Thank you.
Hi, so my name is Krishna Vishwakarma and I'll be talking about comparative analysis of Neo4j versus RDBMS. So as we can see, performance-wise, Neo4j is 50 to 50, 150 times faster for multi-hop queries like finding all nodes within two hops. Neo4j is typically much faster than the relational databases. In RDBMS, such queries become slow and increasingly complex because of the recursive self-joins and deeply nested commentable expressions. Also, on top of that, the new types of nodes or relationships can be added at any time with zero downtime in Neo4j. But in RDBMS systems requires alter table migrations, which can be disruptive and time consuming. Having said that, RDBMS systems will still have the edge in heavy aggregation tasks and integration with mature business intelligence and ETL tools. Group by aggregation queries typically run 2 to 5 times faster in relational systems, especially at massive scale. Thus, we can use Neo4j for highly connected, rapidly evolving, and relation-based analytics, and RDBMS for transactional workloads and aggregation-heavy tabular data. Now, talking about the challenges and the future work, thus the limitation to current graph DBs is because of the slower for complex group by queries and limited to integrations that require graph modeling expertise. Currently, Neo4j is much slower and to tools like BI and reporting integration, and steeper learning curve for users coming from traditional SQL background. Also, scaling becomes also more complex in graphs than in tabular data partitioning. A highly connected network across multiple servers is an open challenge, though Neo4j's fabric and clustering can help them, but it's still a challenge for now. Thus, also using graph neural networks to predict risk based on embeddings, automatically learning which features and pattern signals elevate on emerging risks. Thus the advice to this is the hybrid architecture, which is basically transactional operations stay in RDBMS and analytics and risk modeling happening in Neo4j. Thus recommending continuous investment in cipher training and experimentation to help teams realize the full value of graph modeling would be really beneficial over here. Now talking about the conclusion and the recommendations, I believe Neo4j outperforms RDBMS in relationship-intensive, evolving schema and multi-hop query environments. Thus, Neo4j is purpose-built for connected data, showing clear advantages in performance and modeling flexibility for supply chain, risk analytics, and many more. For teams like teams which are working on supply chain, fraud detection, or recommendation engines, or any domain with highly connected data, I believe graph databases like Neo4j warrant strong consideration. Early prototyping is the key, and I would recommend early prototyping because trying critical queries both in RDBMS and Neo4j to see the difference in performance and query complexity is the first hand to figure out which database to we go for. Organizations don't need to replace everything. I urge that organizations don't need to replace everything. They can keep transactional data in RDBMS and move relationship centric analysis to Neo4j incrementally. The success with graph technology technology depends on investing in team skills, encouraging training in graph modeling and in cipher query language, and maybe taking a hybrid approach of considering Neo4j for relationships and relational databases as well for better transactions. Having said that, that is all about our Neo4j and uses of it for supply chain analytics, and figuring out how relationships can be built and how it is comparatively faster in terms of multiple ways than RDBMS. But we require more of cipher based training, cross functional training, and cipher knowledge being shared to our team members so that we can adapt and make most of use of graph databases. That's all. Thank you so much.